And in this episode, my name is Jacob Scharf, and we'll be discussing the transition from a basic relay logic to a professional-grade, efficient PLC programming in real-world industrial control troubleshooting. Enjoy. Hello, and welcome back to another deep dive into the hidden logic that runs the world around us. I'm your host, and today we are pulling back the curtain on industrial automation. Programmable logic controllers, and what it really takes to move from basic textbook theory to writing efficient, professional-grade PLC code. If you ever looked into the massive manufacturing line, an automated sorting conveyor, or even a synchronized city traffic intersection and wondered, how are all those signals talking to each other without causing absolute chaos? Well, this episode's for you. We're going to break down the mechanics of an electromechanical relay, look at why electrical isolation is non-negotiable, safety standard when you're jumping between low voltage controls and high voltage 480 volt loads, and look closely at how a simple timing diagram turns into a functional ladder logic. But we aren't staying in the simulator later on. We're going to tackle the reality of the field, the kind of messy troubleshooting you run into when the code on your screen has to interact with real live hardware. So grab your coffee, pull up your logic editor, and let's get into it. To understand where industrial control systems are today, we have to start at the foundational level. However, we handle discrete inputs and outputs. In engineering control, discrete just means on or off, true or false, high or low. Think of a basic push button as your discrete sensor and a standard indicator lamp as your discrete actuator. When you start stringing these together, you're essentially building logic gates using physical switches. If you wire two switches in series and you've got an AND function, or both have to be on and closed for the circuit to complete. Wire them in parallel and you've got an OR function. But back in the day, before PLCs took over, we had to do all of this using physical electromechanical relays. An electromechanical relay is a brilliant in its simplicity design. You send a current through a solenoid coil, it builds a magnetic field, and that magnetic field physically pulls an armature. That mechanical movement is what flips your electrical contacts, opening or closing a separate circuit. And that brings up one of the most important concepts in industrial safety, electrical isolation. Because the control side, say a safe 24 volts DC circuit, isn't physically wired to the high voltage load side like a 480 VAC motor. The operator and the controller are completely protected from dangerous spikes in high voltage feedback. Now, when you translate that physical relay logic into a PLC environment like a Siemens or a Koyo platform, things get really interesting. For example, look at a standard traffic light intersection. You've got a 60-second cycle split in a specific intervals. Green 1 running for 35 seconds, while red 2 holds, transitioning to yellow 1 for 5 seconds, and then flipping over in the simulator. You build this using timers and compare instructions, checking if your timer's accumulated value is greater than or equal to 0, but less than 35 to keep that green light active. But here is why the pro side of coding comes into play. When beginners start writing ladder logic, it's very easy to write wasteful code, where you duplicate the exact same series of contacts across multiple rungs just to drive different outputs. It clutters your program and makes it a nightmare to debug. Professional programmers use internal memory bits, like B3 markers in Allen Bradley or M bits in Siemens, to store that logic state once. Then you just reference that single bit wherever you need it. And trust me, a clean code matters, because the real world is messy. Whether you're troubleshooting a stuck motor starter, chasing down a tripped overload block, or trying to figure out why an input isn't registering because a push button was wired normally open instead of normally closed. Implementation is always where the real engineering happens. A well-documented, clean PLC program isn't just an assignment requirement. It's a blueprint that allows any technician on the floor to diagnose a fault and get a system back online safely. And that wraps up our look into relay control systems and PLC logic for today. We've covered everything from the basic physics of a relay armature and electrical isolation to building out time sequences and writing clean, efficient code that won't give your fellow engineers headache down the road. Remember, whether you're working through a lab simulation or tracking down a wiring fault on a physical machine, the key to good control system design is keeping it logical, safe, and well documented. Thank you all for listening in. If you've enjoyed this deep dive, make sure to apply these principles to your next automation project. Keep testing your logic, and I'll catch you in the next one. Take care.